Good morning, everyone. Thank you so much for joining us for another TCIS webinar. This is Mahdi Haddad at the Bureau of Economic Geology. On behalf of the webinar committee, Jiye at University of South Dakota School of Mines and Technology, and myself at the Bureau of Economic Geology, welcome to this 61st ARMA TCIS monthly webinar. Today, we have Dr. Thomas Goebel from the University of Memphis. Thomas is an associate professor of seismology at the University of Memphis. He studies induced seismicity, lab quakes, and volcanoes, and is particularly interested in how differences in fault zone properties affect permeability, stress transfer, earthquake magnitudes, and aftershocks. He received his PhD from the University of Southern California. The title of his talk is Pressure Changes, Rock Deformation, and Aseismic Fault Slip from Laboratory Experiments to Geothermal and Hydrocarbon Reservoirs. We have set up the following two webinars. As you see here, the next webinar is on November 7th by Ben Hansoon at University of Alberta, and his talk is about rupture cascade initiated by wastewater disposal, nucleation, and domino effect of the 2022-2023 earthquake sequences near Peace River, Alberta. And the next webinar is by Men Andrin Mier and Valentin Gischek from ETH Zurich at December 5th. And the title will be determined later on. So some logistics about this webinar series. Please feel free to share the webinar invite with your colleagues who are interested in this topic of induced seismicity. Please contact us if you are interested in receiving notifications for upcoming webinars. And please submit the questions during or after the talk in the chat function at the bottom of the Zoom meeting window and send it to everyone in order for us to summarize the questions or just have better use of time at the end of the webinar. And this meeting is recorded and it will be uploaded in our YouTube channel. Please refer to the invitation email for the link to this channel and subscribe to that for receiving notifications for the future recordings. Without further delay, let's invite Thomas to take over the stage and start the webinar. Thomas, thank you so much for presenting for us.
Okay, thank you very much for the kind introduction. Thank you, Madi and
Thank you.
G for inviting me. Okay, can you see my slides? Yes.
Yes, it is okay.
Okay,
Yeah.
perfect. All right, thank you. Good morning. Good evening, Madi, to you. And thanks for connecting all the way from the UAE and organizing the seminar from the distance. So today I'm going to give you an overview of some of our observations from Oklahoma, and then we'll focus in on a case study in California and then in Nevada. So those two will, occupy most of our time. But a few sort of overarching topics is how pressure changes and rock deformations are connected and how that can induce seismic and aseismic fault slip. I use this term energy reservoir, so this includes geothermal and hydrocarbon. And so the work is done by many different collaborators, but I want to highlight the students and postdocs on the project. Roshan Karala, who since graduated, he's a postdoc with me now. And then Valerian Schuster, he was my postdoc over in Potsdam, and Huyun Guo, she's a postdoc now at Caltech and was a graduate student at UC Santa Cruz. And I would like to acknowledge also the funding. So this is a DOE basic energy science project, and yeah, they've supported the work in Nevada in the geothermal field and the laboratory work that I will show as well. So throughout this talk, I would like us to keep in mind sort of two overarching questions, and we'll unpack and go into more detail. But we're interested in figuring out the contributions of direct pressure versus proelastic effects, and especially if we have very spatially large scale and high volume injections. And as a seismologist, this does change the equations for the seismic hazard assessment. And I will show that if we include the porolastic effects, there's certain contributions at large distances and depth that are problematic for induced earthquakes and corresponding hazard. But also right after we do some changes in the operations on the injection or production sites that can actually affect the earthquake rates. And so this is kind of tying then into the second question, what causes induced earthquakes during rapid operational changes? So we'll show some observation that has been reported now in several different geothermal reservoirs, and then we'll look at a model that could explain that. Okay. All right, so just to set the stage for those of us who don't maybe think about induced earthquakes on a daily basis, for me personally, there are a lot of surprises of related to the observations that we have with induced earthquakes in the southern Oklahoma and in Texas. And here are the observations. So focusing first on Oklahoma. Where the blue ones are wastewater disposal wells in the Arbuckle Formation, and then these magenta and red circles are earthquakes. So we see there's an early ramp up of injection activity towards later 2007's 8th. Then, of course, we had a very productive earthquake sequence in 2011, which was magnitude 5.7, the Prague event. And we see an overall further increase in wastewater disposal activity, so saltwater disposal that was surfacing from produced oil. And we see that the earthquake migration basically follows, at this large scale, follow the spatial pattern of where the wastewater disposal is happening. So for me, it's just, I like to show this picture because the sheer scale of this is unexpected, right? It's very surprising that sort of at the scale of a whole state, we can perturb the earthquake rates. As a seismologist, right, we don't really have a comparable observation, except now, I would say, in Western Texas, right? And so just the sheer scale, number of earthquakes, magnitudes was unprecedented at the time. 2016 was early 2016 that we had the peak rates in terms of earthquake activity, and including Fairview earthquake and then the Pawnee and the Cushing earthquake all in the same year, all magnitude 5 events. Fast forward now and going to Texas in the early 2020s. So Oklahoma had about 5 plausibly, most likely induced events that were above magnitude 5. Texas now has 8. So most recent was in 2024. It was a repeat almost of the 2011 Prague event in Oklahoma. And Texas has sort of consistently, Western Texas, really the Permian Basin, really, has consistently produced these magnitude 5s starting in 2020. And predominantly from, as I said, so here in Western Texas, Permian Basin, including also southeast New Mexico. And there are these persistent seismicity clusters that are producing earthquake up to, and above magnitude 5. Okay. So we have these 2 observations. So let's go back, I guess, and look a bit at what we classically, or before I do that, let's just reiterate this point, how initially at least surprising these observations were, at least for the seismologist side, right? The conversations were more so, aren't they likely to be natural at this scale and also at this depth? And this was, in 2013, an interpretation that best fits the current data is that the Prague earthquake, the first one in 2011, was the result of natural causes, right? It was just based on the understanding at the time, which sort of evolved then over the following years. And part of what the understanding shaped was the early, very impactful study by Rayleigh et al. In 1976. at the Rangeley, Colorado site. So an experiment in earthquake control at Rangeley, Colorado was a very targeted injection type experiment to raise the reservoir pressure above a critical value and to turn the earthquakes on and off, right? So the details are important. So the overall correlation is very striking, right? So if you drop below this critical pressure, then the earthquake rates decrease or they even get shut off completely. But I think it's important to reiterate how large, relatively speaking, now we'll show a slide in a minute, how large these pressure perturbations were, right? So 5 to 10 MPa, and this is similar to stress perturbations and or effective stress perturbations in the lab that we need to induce stick slip. Now, if we fast forward and then compare this to Oklahoma, I would say the pressure changes were tiny, right? Several orders of magnitude smaller. And this is from work by Karanen et al., published in 2014, and showing that if we try to model out a simple, layered media and just focusing on pressure diffusion as a dominant process, you can then sort of map out what the pressure perturbation would look like at each of these hypocenters. And you see you have a mode here that is around 0.07 MPa. So tiny, right? Nothing that we could use in a lab, in fact, to produce to create unstable slip, because these pressure perturbations are just too small, right? And so why? And we'll go into more modeling results here in a minute. But what are some of the underlying observations that uh, um, make it very likely that whatever pore pressure or elastic stress perturbation we have, it's likely to be a very small magnitude, right? One key driver of that is because the earthquakes, and this is focusing in on Oklahoma now, the earthquakes are very deep. And we see that they're highly correlated with injection rates. The left-hand side is the time series between 2008 to 2017, showing the increase in injection and then the decrease. And the earthquakes follow this pattern, at least if we do sort of a low pass, so to speak, on the earthquake rate. We see both the increase has about a 12-month lag, and then the decrease maybe a little bit less. But they show a very similar pattern to what we see from the injection. So, we think there's very good evidence that most of these events are induced, but they are happening much deeper than the injection zone. So somehow we have to transmit pressures or stresses to these depths so we can perturb whatever the faults feel at these large distances in depth, right? So one plausible model that's a slight modification of the Karanen model is to include fault damage zone and argue that, well, for maybe fault damage zone are just these high permeability pathways, these highways that rechannel the pressures from the injection zone down to depth. And this is based partially on our understanding of fault damage distribution, fracture density, and how that should affect permeability. We will go into details when I talk about our lab results here in a minute. But if we feed this into numerical models, we can indeed see that including high permeability pathways can pull down these pressure perturbations to significant depth, right? So this is an earlier work by Zhang et al. Published in Groundwater in 2013. It's at least one of the earliest studies that I found using finite element. There's an earlier work that argues for the same model by Shea and Breda-Heft in 1981, although they still argue for much higher pressure perturbations required to induce earthquakes. So I think this has basically now been widely accepted that the pressure or stress perturbations to induce earthquakes are very, very small. Okay. There's at least some observational evidence that this could be a viable model, right? So this is a study here from Texas where the seismicity distribution seems to extend down from the shallower Ellenberger dolomite Ellenberger formation where injection happened, and then down into the basement where we tend to see more and also larger magnitude earthquakes. We had our own study, very similar in 2016, looking at a potentially induced earthquake sequence, the very central part of the Central Valley, where the basement is a bit shallower than in other parts of the Central Valley, and a reasonable kind of systematic migration of seismicity away from wastewater disposal wells. And if this hypothetic, we hypothesized if there is a high permeability highway that connects the well and here it's the White Wolf Fault, there pore pressure could be an explanation for the earthquake occurrence, induced pore pressure perturbations, right? But whatever we do with the hydrological model, right, the perturbations are still very tiny, right? So within order of magnitude, depending on what permeability you tie in. Now, let's look at potential contribution from poroelastic stresses if we include them in addition to the direct pressure effects. And so I have to click on this one, otherwise it doesn't allow me to forward the slides. Okay, so we'll start with a case study here in Central California, where we had a very rare and interesting observation. This is one of the most spatially temporal correlated seismicity sequence to an oil and gas field that I've seen. And so I said, we're here in close to the coastal ranges, Central California, in the St. Ardo oil field. It's a small oil field, but it's probably one of the youngest, starting operations in the late 40s. And we're located just about 30 kilometers west of Parkfield. So this is San Andreas Fault and the Parkfield segment, and we're just actually talking to my group this morning about Parkfield earthquake. So this juxtaposition between the San Andreas Fault and this, likely induced sequence is obviously also quite interesting. But okay, so just looking at this map here, right? We have wastewater disposal wells, and then we have spatially closely associated an earthquake cluster, reasonably productive earthquake cluster. One interesting point is that so the operations okay, it was 49, I think, was early discovery, but operations started around 52. And right after that, there was a sequence of earthquakes that is reported in the catalog, up to about magnitude 5 or so. Admittedly, the location uncertainty of these events is very high, so it's hard to say one way or another if there is a clear correlation. But we used the more recent data and analyzed this in a bit more detail. And one aspect that we wanted to include was surface displacement. So if there is a poroelastic effect, maybe it could be imaged with surface displacement. Menno Shirsey had showed this before for Texas, that this is a good measurement to use. And so Menno actually created this map of surface velocity, line of sight velocity from INSAR, and he tied it in. So each of these dots is a different GPS station, so to verify that our measurements are reasonably accurate. And so two things that stand out, right? This obviously we see the San Andreas fault, right lateral fault. So we have a clear difference in deformation pattern. But the other signal that stands out, with what we just discussed previously, is this uplift signal. We interpret as an uplift signal towards the center of this wastewater disposal activity in the St. Ardo oil field. And so the total, this is now cumulative displacement between 2016 to 2020 was almost 60 millimeters. Okay. So right where we have this red patch. Okay. So what could be the reason for that? Well, if wastewater disposal does indeed perturb and change the reservoir pressure, this also causes a poroelastic expansion of the reservoir. And this works basically in two ways. There's a direct uplift signal that we can, similar to if we overproduce a reservoir and we get a drop in pore pressure, that could lead to subsidence, which has been reported very widely in oil and gas industry. So increasing the reservoir pressure could cause an uplift, and then we have this pattern of in the radial direction dilational strains and compressional strains at close to the well and then at larger distances, right? So at least this uplift pattern seems to fit, the interpretation that there is a pressure increase, and then implications would be that we also have elastic stresses that are compression at larger distances. And we came up with a simple, just layered finite element model to link the pore pressure change and then the spatial pattern of the proelastic stresses, and this is shown here. So if we have a cap rock, we're basically isolating the pressure pulse within the reservoir, and we just have a little bit of pressure diffusion into the basement. We can look at what the pressure and the elastic effects would be in the targeted zone and then beneath. And so this is showing a 2D slice here, where we see this transition from more dilational near to the well to compressional. But yeah, so the interesting part is if we just look at sort of transect profiles away from the well, we get a reasonable elastic stress response in the basement, and this, even at large distances, up to about 10 kilometers, even just a few days into the injection cycle, right? And important to look at the Y scale here, right? So these are tiny stress perturbations, but this is just a hypothetical scenario of 51 days. Obviously, if this is continuous injection and this is a field-wide, these stress magnitudes would increase, but you can see very quickly that we may reach values that could exceed what we saw from a pure pressure diffusion model. Okay. Now, we looked at the temporal pattern. So this is a zoom in of the St. Arda oil field and the seismicity cluster. And we just did a cross correlation of the wastewater disposal rate between the late 70s until about 2017-18. And the red is the seismicity. So we see a fairly good, correlation. Correlation coefficient is about 0.71, and it's distance dependent, right? So if we include this seismicity, it seems to be very correlated. If we include San Andreas fault seismicity, then the correlation starts to decrease. So that's plausible, I guess, if we think that this is induced and this is more related to a tectonic process. What we also saw that the spatial pattern roughly corresponds to what we expect for basically a finite proelastic source that has an elastic stress halo that decays as 1 over r squared, right? So this is epicentral distances. So this is kind of a plausible stress decay that should plausibly match these epicentral seismicity density. So the red is the observation, and then this black solid line is roughly what we would expect from the elastic stress. Okay. And we went a little bit further and also explored this spatial seismicity decay for many different injection sites where the injection wells were isolated, and we could really measure the distance from a single injector to all of the earthquakes. And so this is what we found. So this is a lot of geothermal and scientific side included here, and also some oil and gas. But we found two different types of spatial decay highlighted in blue and in red. One that looked a bit more Paula-like, and one that looked more truncated, where we get a more rapid decay. And a potential explanation is that certain sites are more dominated by direct pressure effects, and other sites have more of this elastic stress halo. And of course, this is an issue if we think about seismic hazard, because, well, we may perturb stresses at faults that are pretty far from our injection well, and we may need to think about these faults that are out to 10 or more kilometers from our injection site. Okay. And the slope here, the exponent, is a little bit larger than what we saw before. And so, there could be other processes that are contributing, potential event interactions. Earthquakes are very good at causing more earthquakes. We know this from main aftershock sequences, and this may play a role in perturbing this exponent. Now, let's bring these things together, right? So the first question was the relative contribution of direct pressure effects versus proelastic effects during induced seismicity sequences. And I think, INSAR surface deformation is a very good tool. So combining the seismicity and INSAR really highlights that there seem to be far-reaching coupling processes that can induce earthquakes, even below the injection zone and also laterally at large distances. And we saw that the spatial seismicity decay roughly agrees with the expectation from elastic stress decay. But clearly other processes may also contribute or may be able to explain the spatial seismicity decay. And going into problems and caveats that will motivate the second half of the talk, right? The numerical models were used to infer stresses and pressures, so it's obviously not a direct measurement, and so there's still a good amount of uncertainty involved, right? So it's inferred indirectly from numerical models, and then the hydrogeological and the proelastic properties in these models, they may be reasonably constrained within the reservoir, but if we're trying to go out to 10 kilometers or more, we usually don't have any data. So we have to kind of take our best guess or work with the end member models to constrain these processes. So particularly the second component motivated our study in Nevada in geothermal, in the Blue Mountain geothermal reservoir. And the idea was to have one natural laboratory where we can test and measure these properties in a lot more detail and then see if they can inform our numerical models and our process understanding in terms of what drives induced seismicity. And just to set the stage a little bit, so Blue Mountain, the geothermal reservoir, is located about it's about 3 hours north of Reno. It's a binary geothermal power plant and has a gross production of up to about 50 megawatt and started operation in 2009. And our industry partner is Circ Energy. Was very pleasant to work with them. The power plant has since changed ownerships, but we're still working with Circ, and they've been a great partner on this project, as well as DOE, as I mentioned at the beginning. So an interesting fact about Blue Mountain. So those of you who are following the geothermal news, right? Blue Mountain was the prototype for the Fervo energy, the hydraulic fracturing operations, and the proppant injection. And so my student, now postdoc Roshan, we were there when they prepared and did their hydraulic stimulations, and we saw the very large water tanks and the operations that you have a drill rig over here. And this is the actual power plant, of course. Okay, and this is just again to show the work by Fervo, which now extended out to Utah, where they have their first kind of pre-commercial power plant that's, I believe, starting or is already starting operations. But yeah, in Blue Mountain, it was the first test site to see if one could drill in very horizontally and do hydraulic fracturing jobs in very hot environments. So this has a geothermal temperature contour of about 180 degrees. So 2 laterals, hydraulic fracturing, and trying to connect these 2 wells to produce, to inject cold water in one and produce hot water on the other side. Okay. And just one word about seismic hazard, right? It is important that these type of stimulation could potentially induce earthquakes. The process is very complicated, but there is some work and papers on the Pohang earthquake sequence in 2017. That was a maximum up to about moment magnitude 5.4. And so this earthquake may have been triggered or potentially been induced by geothermal stimulation. It's a complicated story because the earthquake happened more than a month after stimulation ceased, but the seismic hazard, I think, is important to keep in mind for these type of stimulations, and it is a probabilistic framework, right? So there is a non-zero probability that high pressure stimulations could have implications for seismic hazard. Now let's dive into our study. And as I said, we wanted to have a more holistic view and do a lot of different testing and see if we can inform our models. So we did core testing in the laboratory. We're partnering with GFC Potsdam to do the lab testing, and Valerian Schuster had the lead on this component. We measured permeability in situ. This was led by UC Santa Cruz. And then we had the lead on the seismicity and on the surface deformation here in Memphis. So I'm going to show you a bit from the lab deformation, the seismicity, and then also from the INSAR. The INSAR had a very clear, good signal. So this is work by Roshan Kairola, and he found, in correlation also with Mano Shirsey, he found that there was a clear subsidence signal. So inverted from what we saw in St. Ardo. And we have the power plant here in yellow and the production wells. And you can see this slightly elongated ellipse. Here's a close-up. And if we take a profile across, we get maximum surface velocities of about a centimeter per year. And this is using different satellite tracks, so we'll isolate the horizontal and the vertical component, and so the vertical is about a centimeter per year max. And Roshan looked at a bunch of models that could explain this signal, and it seems to be a combination of temperature and potential aseismic slip on this normal fault that best matches the pattern that we observe. And maybe a prolastic component, but it could be really secondary for this long-term effect. And he did a rough energy budget and arguing that the geodetic is sort of so this is basically the observed from the INSAR. Geodetic is much larger than seismic, and seismic, we see this in a minute, has a very minor contribution to the release of stored elastic strain energy for the Blue Mountain field. Okay. So before we go into the details of the seismicity analysis and then also the models, and I have to keep the time, I think we're okay in time. I do want to show the lab results, which were very intriguing and turned out to be much more complex than I anticipated. And as I mentioned, this was work by Valerian Schuster at GFC Potsdam. So the primary lithologies in Blue Mountain are these felsic intrusions and metasediments, mainly argillite and phyllites. And we have both fractured and non-fractured versions of these rock samples. But the key story is related to hydrothermal alterations of these cores. And I will show that here, at least part of the results in a minute. So Valerian went through this procedure of preconditioning and testing and measuring permeability and B-Willis coefficients during different steps in pressure. So both the pore pressure was modified and the confining pressure, and then we looked at the effect of different effective pressure on permeability. And then we also used that to look at the volumetric strains, which was used to compute the B-Willis coefficient, the coupling coefficient. Just real briefly, this preconditioning was actually very key because these samples were exposed to atmospheric pressure for a long time. So to basically get rid of some of these nonlinear effects, the preconditioning kind of helped us with the accuracy of the measurements. Now let's look at permeability, and then we look at the deformation signal. And as I said, the study turned out to be more complex than I anticipated, so I don't have time to explain everything. But the the cracks in the hydrothermal alterations are key. And we saw both two terms of hydrothermal alterations, the decomposition of feldspar to clay, and clay minerals were very important both for the compressibility and the coupling as well as for permeability. But then also silicification, especially along fractures and open fractures, were really important. Okay. So shown here, just two kind of first order observations. We don't see any correlation between permeability and porosity. And so this is, reasonably common if, let's say, fractures are the dominant means to promote fluid transport in the rock. And indeed, we see, right, if we isolate this a bit more, permeability as a function of effective pressure for these phyllite cores, ones with closed fracture, shown here at the bottom, and then the very top is with open fractures. And this is core that is just separated by, a few tens of centimeters. So it's almost the same interval. But the presence of these open fractures, even after this conditioning, and you see for these various effective pressures, really increases the permeability by many orders of magnitude, 5 orders of magnitude. Okay. And we do see a bit of a sensitivity because of the shape of the fractures, right? And these high aspect ratios then make them also more susceptible to effective pressure changes or starting to close up some of the cracks and permeability drops. Okay. So this is the first one here. And now we also looked at pore-elastic coupling and the heat transport, thermal diffusivity of these rocks. And, again, there's not quite enough time to show you all of the details, but we saw that this hydrothermal effect and the presence of cracks also really affects how compressive and how much the Beer-Willis coefficient changes with effective pressure. So let's just look so we have the highest pore-elastic coupling coefficient for the massive phyllite. And then, so this is shown in orange. This blue star was the sample with the open cracks, which was hydrothermally altered. And we saw a lot of evidence for licification. And so there is a slight dependence of Beer-Willis coefficient on effective pressure. And the closed fractures, highly silicified, they tend to be much less coupling, and Beer-Willis is independent of effective pressure. Okay. So overall, the implications are, right, so if the geothermal reservoir is primarily comprised of these fractures, we could see a lot of reduction in permeability and potential, if it's a large enough volume, potential surface subsidence because of pore-elastic coupling and because of pressure reduction, right? And the last point here from the lab is that silicification actually increased the thermal diffusivity, quite significantly compared to the other samples. So we have these competing effects, right? If the operator would ask, so what's the best geothermal reservoir? It's hard to say, right? Some of these processes, fracturing, increasing permeability, but the high aspect ratio also make it more susceptible to effective pressure changes, and we have high pore-elastic coupling. These interlinked processes make it very complicated. But just a few implications from the lab test, right? So it looks like partially silicified cracks increase permeability, and they also really ramp up the heat exchange, the thermal diffusivity. So for a geothermal resource, the overall degree and level of hydrothermal alteration is important to understand. And we haven't even talked about the effect of clay, which is in the felsic intrusion is a key component, which we didn't have time to discuss, right? And so the fractured reservoirs are very sensitive to pressure changes, and this could reduce long-term production, right? Now, to finish off the talk, the last thing I want to discuss is the seismicity that we observed in Blue Mountain and what we think is responsible for the seismicity. So this was the the seismic network. We had access to about 8 stations showing in black here. This is an exemplary waveform and spectrogram of an earthquake recorded in Blue Mountain. Spatially, there was a close correlation between the operational activity and the seismicity. So both in terms of lateral, but then also depth interval. You see the cross section here, south, north, and west, east. The seismicity roughly happening at injection depth, which tend to be a little bit deeper. Now, one very interesting observation was these vertical. So this is a time, magnitude over time. We had these vertical lines here. So these are events that happen very rapidly. So an increase in rate. So we looked at this in more detail, and we found that these seismicity rate spikes were correlated with maintenance shutdowns of the geothermal reservoir. So when the pump stopped, it was about 24 to 48 hours for repairs and checking pipelines and whatever is done during maintenance. And this caused an increase in seismicity rate. So we can zoom into this BC here, and we see that this is a 2017 shutdown. We have the seismicity peak more towards the end of the shutdown, and here in 2018 it was more towards the beginning. So we used a model originally proposed by Siegel and Liu in 2015 that incorporates pore-elastic coupling and time-dependent earthquake nucleation in a rate and state friction framework to explain what we saw, right? So it's somewhat counterintuitive during the shutdown. We don't expect any pressure increase, at least close to the injection well. So having a spike in seismicity is somewhat unexpected. It's usually during the injection or even production sequence that we think induced seismicity is more plausible. But if we use this model that looks both at direct pressure effects and then how pore-elastic stresses are changing the shear stress and the normal stress on optimally oriented fault, we get this spike in the Coulomb failure stress. And so the reason for that is really that pore pressure and the elastic stresses, they're operating at different time scales. So at a large enough distance, you could still have faults that are highly pressurized, but the normal stress, which, the pore-elastic clamping stress in this particular tectonic regime is reduced a lot more rapidly than the pore pressure is reduced because, it's a diffusive time lag. So both in time and in space, we have this narrow range where this peak in stress or stressing rates could cause seismicity. And this seems to roughly match what we saw from the earthquakes. So the red is the pore-elastic model with rate and state, and the black dots are the observed seismicity rates. And we have the initial peak is a bit steeper, and then we have a more gradual decay, which may indicate that there's some heterogeneity either on the frictional side or on the hydrogeological side in the reservoir. So the near field response a little bit different than the far field. So this was the temporal, and we can also look in space, and this is quite, I think, instructive to untangle these two processes, right? So both for the 2017 and 2018 shutdown, we have these two panels. If we only look at the pore pressure effect, the injectors, have a rapid drop in, and this is just looking one day out, right? So the dominant signal is just really the drop close to the injectors, and there's a modest recovery in the production wells, right? So if you're pumping wells and then fluid flow is towards the well if it is a producer, and if it's an injector, it's the opposite, okay? But nothing really seemed to be happening where the earthquakes were. Now, if we include the pore-elastic effect and we model this for the given tectonic regime, we see azimuthally dependent pore-elastic stresses that are elevated at larger distances. So there's a finite distance range where these are increased, but we see that the earthquakes fall within the contours of Coulomb failure stress increase. And so they could be responsible for the observation of these seismicity spikes right after shutdown. Okay. Now, so the takeaway, right? So if you rapidly shut down your injection well, you may get this short-lived, basically elastic stress pulse, and the underlying stressing rate changes can cause short-lived seismicity bursts. Okay. I do have to say, right, the seismicity we observe, I should have mentioned this earlier, the biggest event was a magnitude 1.5. So these are very small events. So we didn't see we didn't record any failed events. And certainly the overall contribution of seismicity to the total deformation budget is very small, as I indicated before. Okay, so to conclude, um, this section, right? So just 2 points. So the spatial seismicity decay and distant and deep induced events may be related to the more far-reaching poroelastic stresses that trigger these earthquakes. So we've seen this for the global study, then also in California. And Blue Mountain, one key takeaway is that if you have a highly, you have a high Willis coefficient, you have very efficient poroelastic coupling. In that case, rapid injection rate changes can trigger earthquakes sort of immediately after the operational changes. But we also saw that the contribution to the total deformation budget is very small, at least for Blue Mountain, right? It's just one case study, um, and it's too early to extrapolate out from there. Okay, thank you. That's all that I have for today. I'm happy to take any questions.
Thank you, Thomas. Great and thought-provoking webinar. It was a lot of content. Thank you so much. The questions, I think the first question is actually directly he requested to ask it from you. It is from Peter Eikebel. Peter, if you want, you can unmute yourself and ask it.
Yes, Thomas, thank you very much for this presentation, and in particular for addressing poroelasticity, because it seems to me that there are two camps in the community now, the ones that strongly emphasize poroelasticity, and then there's this other camp with lots of publications recently that completely deny this topic. So I don't know, but and obviously I'm in the first camp, right? My question is, when we applied for wastewater injection in porous reservoirs, I think we agree the poroelasticity is a small part, but it's a significant part perturbing the stress field, especially when it comes to deep basement-induced earthquakes, right? At one point, we looked into the thermal effects of injection, and this is not in our papers, I believe, but we concluded those are just near whale bore effects, and we can neglect the thermal elastic component. However, when you take this now to geothermal, I'm not sure if you can still neglect this. And you were talking only about poroelastic effects, but we can obviously lump thermal and pore together, but we have to be cognizant that thermoelastic effects do not require a lot of permeability, or it can be purely conductive, actually, right? And it may behave at different characteristic timescales than the poroelastic effect. So, and I guess to phrase the question to you, have you considered including the thermoelastic stress changes, especially when the field is in longer production, right? When thermal effects become more widespread.
Exactly, yeah. No, great point, great point. So yeah, we have looked at long-term thermal contraction and basically trying to link it to the long-term subsidence, and that could be a factor. So, it's also complicated, right? So your assumption, whatever assumption you make about the geometry of the reservoir will be key. If it's a more localized reservoir, you're generating fluids through a narrow zone, that will affect how much of the volume you're cooling over a given time frame in the absence of direct measurements, right? But so what we found was that if we're basically cooling a large enough volume, even just by a few degrees, I think 3 or 4 degrees Celsius, you can actually have sufficient contraction to explain the 1 centimeter surface subsidence, right? So this is long term. This is, and you mentioned it too, it's a long-term effect. So short-term variations in seismicity will be hard to explain by the thermal, but the long-term deformation pattern could indeed be thermally, just thermal contraction of the rock. You're just cooling, whatever, 1 cubic kilometer rock by a couple of degrees. That's sufficient to, shrink, have subsidence of, a centimeter or so peak at the surface. Now, yeah, the thermoelastic effect and potential implications for seismicity, we have not looked at that, not in Blue Mountain. I know there's a study in the geysers and also in COSO, and they tend to lean more to that. It's not a big component in terms of seismicity triggering, but I cannot, I guess, fully speak to that. But what I can say, long term, yes, thermal certainly. The short term, I guess we would have to look a bit more in detail how those stresses could affect the stability of faults and potential triggering of earthquakes.
And if you say not a large component, that sounds like the people who say that about pore elasticity too, right?
Yeah.
Component, but it's significant, right? Like it tips the balance, right, at the end. So I don't know.
Yeah. No, I agree, and I just would have to look into. We haven't really computed or calculated the thermoelastic stresses, and to give you, I'm being a bit cavalier about other people's study, and I shouldn't. So it's what I should say is we would have to look a bit more in detail to see how important this effect is. Yeah.
Thanks. Yeah.
Awesome. So the next question is from Jige. And first, he thanked for the informative talk. And his first question is about basically Oklahoma case and Colorado. You mentioned that the small pressure change can cause seismicity in Oklahoma. The faults are deeper, hence more close to the critical state, or due to poroelastic state change. Basically, those are small pressure changes cause earthquake. Is that either because faults are deeper, hence more close to critical state, or basically the stress is larger, or due to poroelastic stress change? What is the case?
So I think that one question was about the magnitude of pressure
yeah.
perturbation in a sense, right? So we compared Rangeley I would say that was a very specific type of experiment, and maybe it's not quite clear how representative that experiment is for, the shallow crust if I would say observations from Oklahoma and Texas clearly indicate that small perturbations are enough to cause seismicity. I think that point is very well established. Now, and it agrees what we know with aftershock triggering, right? The Coulomb stress changes, the static stress changes, and dynamic for that matter, that cause aftershocks are really small. So then it's a probabilistic type of assessment, right? If you change stresses over a large enough area, you will encounter some close to critical fault that will produce a seismic event. The second question, if the deep is more likely to be pore pressure or poroelastic, I think these are kind of the alternative models, right? Either you have this permeable zone going down, and I see, and you need a very specific hydrogeological structure to channel pressures to these large depths. Or alternative, it's the elastic stresses that are communicated to large depths. Either way, it's hard to have direct measurements. We try to tackle it from the INSAR side to argue, okay, there is some rock matrix deformation that is coupled to the initial pressure effect. But like Peter said, right, I think there are different camps out there. I'm leaning more towards the poroelastic because I haven't seen that evidence fully developed for these high permeability fault zones. And it would have to be pretty pervasive and basically everywhere where we see these and it's the other component that kind of trips me up, right? If we do these tests in the lab, it's pretty much impossible to keep this permeability at very high values once we start squeezing the rock, right? And so we're talking about going down to maybe 5, 6, Oklahoma at times 7 or so kilometer of hypocentral depth. It just becomes very hard to argue for these high permeability pathways. Fractures have high aspect ratios, so when you start squeezing on them, they tend to close up pretty quickly. So you need some mechanism in addition. You need fractures and something that keeps the fractures open, even when you squeeze on them very hard. But yeah, I mean, as I said, Peter mentioned it. The jury is still out. I think we have two different camps. Better observations always help, right? So that would be my
Exactly.
view on it. Yeah.
His second question is about temperature and potentially rock fluid interaction on the permeability decrease. So basically, imagine we have a geothermal case that leads to induced seismicity. We have a highly permeable pathway for the leakage of the fluid to other layers. So if it happens, then is that geothermal case dead because you have not any isolated fluid pathway? You may leak a lot of injected fluid to overlying or underlying layers, and basically you don't have a closed case for the fluid to get in and get out. So how about the rock fluid interaction for the permeability decrease in this case? How can we rescue the geothermal field in this case? Basically,
So
it's just some extension of what he asked.
okay, interesting. So I guess that would be more towards the conventional geothermal, or
So
yeah. So
EGS,
oh, in EGS. Okay. Um, EGS, I'm not sure. I'm not sure if anybody quite knows the answer to that yet. I could say I agree, right, that that will be an issue both from the chemical processes and potential increase of the fracture network that will increase the fluid loss. I think that was part of the question, right? Um, and fluid loss, it could reduce the production rates, and so it's a bit more speculation at this point, I would say. I think we'll know more soon. What I can say from the observational side, right, in Blue Mountain, the conventional, pressure maintenance is an issue. Blue Mountain was more an issue with not cooling the rock. That's not the right, but not channeling the fluids too quickly to the producers, right? And there was permeability being too high, or injectors and producers being too close to each other, then you have reduced production temperatures. So there are many potential issues in geothermal to have, also long term, right? You want to operate over 10, 20 years and have similar production rates without having to reinvest and moving your wells around a lot. And so the chemical processes are a problem, permeability evolution, kind of short circuiting your injectors and producers, all of the above. I agree that the issues may exist, and for EGS, I just don't think we quite have the data. And conventional, yes, I think that's a repeated issue, that you're producing cooler and cooler water because of these processes. Yeah.
Perfect. Thank you. So I see no more questions from the audience. So if anyone wants to ask question, they can unmute themselves and ask it. We have 1 more minute to reach to the top of the hour for this webinar. So please use this chance to ask the question directly from Thomas. Someone asked a question. Okay, so the next question is from Paul Freiberg. Paul, do you want to unmute?
Hey, Marty.
Yeah.
Yeah, I'll unmute. Yeah, so I just wanted to comment. So we've seen cases in Ohio where we do have high permeability faults, that we can link directly to stages that cause within minutes, and I don't think the poroelastic effect could be, so there are cases out there. I just wanted to let you know that we've seen cases where certain stages can, cause seismicity almost a kilometer deeper than the stage itself. And the only way that could possibly be happening is if you have a high permeability pathway that's already fluid filled and you're just pushing on it from above. I don't think a poroelastic effect is taking place there. Mike Brzezinski might argue that there are other faults in Ohio that don't do that, but we've seen a number of faults that are high permeability. But these are direct injection cases that we're seeing this sort of thing.
So Paul, that's interesting. Is that from hydraulic fracturing? And you're saying you have an observation of some stimulation, and then you have earthquakes that are a couple of kilometers below?
Yeah, at least a kilometer below in the basement. So so at least 3,000 feet below the formation being fractured. So we can tie it to individual stages because the laterals cross this structure that seems to be the pathway, and they light up when the stage gets to that particular crossing point, that seems to fire off more earthquakes in the basement. So there are cases where there are highly permeable fault zones that are probably already fluid filled. I'm not saying that frac fluid is getting down to basement depth, but it's probably a case of a pipe that's already filled and just being pushed on from the operator.
Yeah. So you said about a kilometer down.
Yeah. Yeah. So anyway, I just wanted to highlight that. Yeah.
No,
Great
good.
point.
Thanks.
Yeah. So great talk, Thomas. Thank you so much.
Thanks, Paul. Yeah. Good to hear.
One thing to consider is pressure front can be far ahead of the actual fluid front. It is great point that Paul raised. So basically, the entire fluid pathway can be full of fluid, and the actual hydraulic fracturing fluid that you inject is not reaching to the hypocenter, but the pressure front is far ahead of it. And you start the activity just because the pressure is just rising because of injection close to the fracturing stage. Yeah.
Certainly, but the time scale is still controlled by your hydrogeological parameters, permeability and storativity. There's still there's basically a speed limit determined by those two parameters. But yeah, very high.
Yeah, I mean, we've seen it within 30 minutes. So, I don't think the permeability will allow. So, my hypothesis is that it's a pressure pulse. How can I prove that? That's a tough one. I'm afraid I have to jump to another meeting, but thanks, Thomas. This was a great talk. I really appreciated your thoughts on all this stuff. Take care.
Thank you so much.
If it's shallow enough,
Bye,
we could drill into it. It might resolve, it's a very interesting observation. We could resolve it that way, potentially.
Exactly. Okay, great. Thank you so much. So we are on top of the hour and 3 minutes after. So basically, thank you so much, Thomas, for presenting for us. Thank you, everyone, for joining us. So the next webinar is on November 7 by Wenhan Soon, and we look forward to seeing everyone over there in the next months. Thank you, and have a good day and have a good evening, depending on where you are joining us. Thank you. So if you have time, you can just spend some extra minutes with us to answer some of the questions if people want to ask some questions informally. But other than that, thank you so much for presenting this time.
Yeah, thanks.
Thank you. Very interesting.
Yeah. Yeah, these are some hard measurements to make, but it's always nice to have combine it with observations from different settings. Ohio, and I know up in Western Canada, they also have very interesting seismic responses to hydraulic fracturing.
Exactly. It looks like people ran out of questions. So we can close the meeting if that is fine. But this is the last chance for everyone to ask questions if they have any questions.
So let me ask you, are you going to have an induced seismicity session at the ARMA meeting? Or is
Uh,
it
I think there is, but I need to
Yeah,
recheck it. Yeah,
I see. Yeah. Very
I
nice. Yeah.
think Sean Maxwell organized that last time,
Yeah.
but
Right.
probably he's organizing the same thing this year. But
Yeah.
yeah, I need to recheck.
Okay.
Yeah.
Yeah.
Are you going to join this year for ARMA Symposium?
I have to see. Yeah, I would like to, if possible. You know, it's always with teaching and everything, family. You know, I'm sure it's similar for you. Gonna have to
Yeah,
juggle these different responsibilities and things. But you
exactly.
know what? I've never been, so it's kind of towards the top of my list. I've heard
Oh,
it's a very good meeting, and yeah,
definitely.
very
I
nice.
strongly recommend you join at least once to just check
Yeah,
it. It's
yeah.
a diverse set of topics, and
Yeah.
yeah, it's interesting.
How much is there the industry participation? Is it pretty strong, similar to image, or a little bit less? Or
It's less than image, but it is
yeah,
still, I would say, 50%, 30 to
okay,
50%. Yeah.
yeah. Oh, very good.
It's
Yeah,
more academic. I would say
yeah,
academia dominate there, but there is
right.
still a lot of people from the industry. Yeah,
Yeah.
awesome.
Excellent.
Thank you so much, Thomas. I really
All right.
appreciate it.
Yeah. Have a good
Thank you.
rest. You
I
know,
look
rest of your
forward.
evening. You can wind
Thank you.
down.
Thank you. I look forward to seeing you in some events, almost symposium events, maybe.
Yeah. Same here. Yeah, that
Thank
would
you.
be great. Thanks. Okay. Bye bye.
Thank you. Have a good day. Yeah. Thank you. Bye-bye.